Yo, what's up, guys? Welcome to another episode of Live Learning. We're working with PyTorch. In the last couple episodes, we've been doing some data exploration, and we have been what are we doing? And we built like the neural network, and we explored the data a little bit. So now what we're gonna do is we're gonna move towards using. We're gonna learn how to use the AutoGrad. This is a tutorial by PyTorch that I'm just kind of like following, and I'm gonna like comment on it and stuff like that. And I'm gonna drop the tutorial link in below. And let's get started. So we already have Torch imported, but we're gonna start by creating a one-layer neural network. So X is going to be the input. And we use torch.ones, which is torch.ones functionality. Basically, it's just 5 ones. And Y is going to equal torch.zeros, 3. So that's going to be 3 zeros. And W is going to be the weights. And we're going to randomize the weights. And 5, 3. And requires grade equals true. And then the B is going to be biases. Rand n 3 requires grad equals true. Requires, there we go. Then we're gonna have Z equals torch.matmul x w plus b, and loss torch.nn.functional. We're going to use binary cross entropy. Binary cross entropy with logits. Z, Y. So that's going to be our first, basically one-layer neural network. So basically what this does is you take X, you multiply it with the weights, you add the biases, and you get Z. Z is your like output. And then you calculate the cross entropy loss compared to Y, which is the expected output, and you get your actual loss. Yeah. So we need to be able to create, the reason why we have the requires grad here is we need to be able to calculate the gradient of the tensors W and B. So that's why the requires grad is there. So let's check out what the gradient is for Z. Print Z gradient Z. Let's do lowercase z. Z.grad. And then let's also check out what the loss is. Print. Loss gradient. Loss.grad. Let's also just print Z and print the loss function. Dot none. They actually want us to print out the function here. But let's see, it's add backwards object, and binary cross entropy. And that's exactly what they say. So in order to compute the gradients, we need to call backward on loss to get what it looks like going backwards, like the back propagation of neural networks. And once again, I will drop the create neural networks from scratch tutorials so you can understand what back propagation is and how it works. So loss.backward. And then let's also see what the gradient is for W and B. I'm tired. Okay. So this is what we get. We can get the gradient properties for the leaf nodes, which requires grad property, and that's it. And we can only perform gradient calculations using backwards once on a given graph. Okay, let's see what happens. Okay, we don't really need, I don't think it matters if we can disable, I don't know why we would disable gradient tracking. The next step in the tutorial is disabling gradient tracking, and I just don't know why we would ever do that. If we've trained the model and we just want to apply some input data, we only want to do forward computations, then we don't need gradient tracking. Okay, so that makes sense. Okay, so let's just see what happens when we do that. Not no grade. Oops. Mammal xw plus b. Print z requires grad. Now with torch.nograd, we can also do the mammal. So this should just be true and false. Yeah, okay. We can also apparently call detach. So z can equal torch.matmul xw plus b. And then we call z.detach. Yep. We should set something. This returns some the matmul. So z det equals this. And then we can print z det requires grad. And we can print z requires grad. And we should see false and true. Yeah, okay, cool. So the thing that's kind of interesting about the gradients is that apparently torch.autograd is like just what like keeps track of all these things, and like everything is like all the DAGs are function objects, and the leaves of the DAGs. So DAGs are directed acyclic graphs. Basically, it's a tree. And I will drop the post on trees as well in the tutorial, in the comments, not the comments, in the description. And in the forward pass, when we pass data through a neural network, the AutoGrad does two things. It runs the requested operation to compute a resulting tensor, and it maintains the gradient function in the DAG. It retains the gradient function in the DAG. So the backward pass is kicked off when you hit backward, when you type backward, which is right there. And that's the back propagation. And then it computes the gradients from each grad function, and then accumulates them in the tensor's grad attribute, and uses the train rule to propagate all the way to the leaf tensors. And in PyTorch, DAGs are dynamic. Ooh, I'm burpy. So the DAG is recreated every time you the graph is created from scratch. So if you call backward again, you're going to get another graph. So there's also a point here about Jacobian products and tensor gradients. And I'm actually going to go over them because I think that these are interesting, like mathematical concepts that you kind of want to have an idea of. So PyTorch allows you to not compute the actual gradient, but to compute the Jacobian. And the Jacobian is basically if you have a vector y and a vector x, you get the Jacobian matrix, which is the gradient of y with respect to x. So it's the partial derivative of y1 x1 all the way to the partial derivative of y1 xn down, and then down it's the partial derivative of ym x1 down to the derivative of ym xn. And so we can take an idea of what that looks like by basically we'll do this. We will first, so first I'm gonna click here. Yep, okay, so I'm gonna create input equals, we'll probably call it imp equals torch.i 45 requires grad equals true. So let's take a look at imp. So this should just be a series of ones like this. And now if we want something interesting, so the Jacobian, by the way, the Jacobian itself is the vector transposed. The Jacobian product is the vector transposed times the Jacobian matrix. So what we're going to do here is we're basically going to check out what this would look like. So out equals imp plus 1 dot pow 2. So we're squaring the input dot t. And now let's print out. So this is what this looks like. So we added 1 and then we raised it to the power of, so basically everything is added 1 and squared, and we transpose it, which in this case does basically nothing. Yeah. Oh no, because we needed a 4-5. I thought we did a 4-4. Okay. Yeah. So now we have a 5x4 instead of a 4x5. And now if we go backwards and we retain the graph, so out.backward, torch.ones like out. So we should be creating ones, 5x4 of ones. Retain graph equals true. Oops. So let's take a look at what this looks like. Right, 4x5 ones, okay? Now let's see what the input gradient is. So print first backward call on input imp dot gradient. Oops, this needs to be f. Yeah. First backward call on input. And now what we're going to do is we're going to call it again, and we're going to see what the second call looks like. Oh, sorry. So second. So we can see that, you know what? I feel like this should be a new line. No G. Okay, so now we can kind of see what this looks like. Oh, haha, this is actually the third call, so this is second. Well, I messed it up, but this is actually the third call. Because I made this backward call right here. Anyway. Wait, this is beyond, this is foobar. This is fucked up beyond repair. Okay. Anyway, it basically, what you can see is that in this case, what's happening every time is tensors are added to each other. They're doubled. So now let's zero the gradients and see what happens. So imp.gradient 0. That's not right. imp.grade.0. And let's see what, and let's call backwards again. And let's see what it looks like. One's like out. Retain graph equals true. Print f call after Okay, let's also take, so now it's back to what it was before. So let's also take a look at imp.grad function. Print. None. Okay, interesting. Let's look at what out looks like. Yeah, out is this. Okay. And what does int look like right now? Same thing. Okay. When we call backwards for the second time with the same argument, the value of the gradient is different, and this is because we're accumulating the gradients when we pass it back. So in the next thing, what we're going to do is we're going to take a look at the optimizing the model parameters. So we're going to use the data loaders. We're going to build the model, and we're going to train and we're going to test. So that's what we're going to do in the next video. Make sure you subscribe. See you guys later.